Yeah, I'm a third-year grad student at the AMP Lab, and I'll actually be giving this talk on behalf of another grad student, fourth-year grad student named Anand, and he couldn't make it today. But he's been working on some interesting stuff in early things in time-evolving graph processing. And the system that he has is called Tegra. Okay, so the kind of the motivation, which I'm sure is familiar to all of you, is that graph structured data is popular in all kinds of domains. So we see graphs in things like social networks. This is the Twitter social network, a subset of it. In like peer-to-peer networks, in the internet, and then even in diverse domains like biology and medicine. So, and also interest in graph processing is actually growing fast as well. Aside from these sort of reports, there's also been a lot of real open source and research activity around distributed graph processing in the last few years. Okay, but most real world graphs actually change over time, which is sort of in tension with the fact that existing graph processing systems mostly focus on running algorithms on static graphs. And so working with time-evolving graphs is harder, but it's increasingly becoming worth it as people come to expect lower latency analytics. So here's the. Now here's an example of a real time-evolving graph, which is a cellular network. And this consists of a bunch of base stations, and also there are millions of users who are connecting to them and roaming between them. And this cell network graph contains an edge between a user and the tower they're currently connected to, as well as between towers in the same region. And then this graph changes over time as users move between different towers. You can see it change. So, and also one thing that's kind of interesting about this example of a time-varying graph is that it's sort of naturally distributed. So each cell network collects this large amount of log data, and then to process it, it becomes difficult to necessarily bring that all back to one data center. So it lends itself to this idea of distributed graph processing. Okay, but now the network operator that in this example has some important questions that they want to use this graph to answer. Questions like, what did the network look like just before an outage? Are there any network bottlenecks, and how are they changing over time? And where might the network currently be overloaded? So like at this conference, there are hotspots in the real world. And then of course, sort of a general sense of how can we analyze the performance of this network, which is this big time varying graph. Okay, so all of these come down to the question of how we can efficiently compute on time varying graphs, time evolving graphs, and Tegra, which is the system, aims to answer that question. So we can group these the requirements that we need to do this into maybe 4 points. First, we need to be able to access past versions of the graph, which is here are kind of the examples. So in this case, that's just as simple as retrieving the network state when some disruption happened. Secondly, we need to be able to run sort of analytics all the way up to a certain point, and here the example is just analyzing the over time, from the beginning of time or from some existing snapshot all the way to a certain time of the evolution of some kind of a hotspot. And then third, there are these different category of algorithms called sliding window computations. And so there the idea is that you want to track what's been happening just in a particular time interval. And then finally, kind of the general thing that we're always interested in with research on Spark is how do we mix these different computation paradigms, which is one is the graph structured paradigm, and the other is like the more standard RDD or data frame, data parallel model. And that's useful for all kinds of things. And here's one example where you can just generally use this to get all kinds of properties about the performance of the network. Okay, so now I'm going to start talking about the Tegra system and how it's built. So it consists of 4 components. First, there's this graph snapshot index, which lets it manage multiple snapshots of the same graph. Secondly, there's this thing called the Timelapse abstraction that enables efficient temporal computation, meaning efficient computation where you run an algorithm from the beginning of time into the current time. And then there are some actually 2 different incremental computation models, which make it possible to express complex algorithms and then have them run efficiently on both on all the way up to the existing state of the graph, as well as on windowed slices of the graph. So I'm going to explain how these components let Tegra achieve these goals, starting with the first one. So this first one is this graph snapshot index. And how this works is that in the system, Tegra, we represent an evolving graph as a sequence of graph snapshots. And then we sort of assume that these graph updates are coming in a streaming manner. So this is kind of intuitive, where you get a set of updates in the last batch or time window, and then apply it to create a snapshot. So here, in this example, there's like the initial update, which just establishes the graph, and you can see that produces a certain graph. And then maybe there's an update that, say, adds a new node, and adds an edge from A to this new node D. And then we can have the updated graph based on this, and so on. Okay, so one thing to note is that the creation of this delta to apply to modify a graph based on a given time interval actually isn't just a straightforward application of some new nodes and edges. In fact, there's some application-dependent semantics, which is kind of interesting. Here's sort of an example of that. So one concrete example is where you actually might want to reorder or to like deal with conflicts in various ways. One way is you might want the latest update to win, or you might want the earliest update in a time interval to win. And so there's kind of this application level semantics of given a set of updates, how do you apply them to the graph? And then the point of bringing this up is that Tegra actually provides a way for the application to express this sort of merged semantics. Okay, but so now once these snapshots are created, the next thing is to actually maintain them. So this kind of an interesting systems question of how do you maintain many snapshots of the same graph, many versions of it. So here are a couple of strawman solutions. One is that you can just simply store the graph in its entirety, once for each version. So that will let you. The nice thing is it makes it easy to access the graph at any particular point in time. But on the other hand, of course, it's going to be very costly in terms of storage overhead. And then the other maybe strawman solution is that you can just store only these deltas as they're coming in. So you just store the base graph, and then you store a whole bunch of little deltas. Now, of course, the problem with this is that that means that to actually retrieve the snapshot of a graph at some point in time, you have to go back and replay a whole bunch of, some arbitrary number of these deltas. We sort of want something in between these 2 points. And the solution that Anand came up with is to actually use a certain data structure, which is something that I worked on, which is it's called the persistent adaptive radix tree. And the general idea of it is that it's this so-called persistent data structure, which means that it supports updates that actually don't modify the data, but just create a new version. And then it can do this efficiently by using some clever tricks with structure sharing and with laying out the nodes in a special way. And so here's kind of the animation of how this looks. If you wanted to update a certain node within this set of underlying data, then there's actually this tree structure that first of all lets you maintain these updates, and then the update is actually performed not by modifying the node in place, but rather by copying it and all of its ancestors. And so this gives you these two different versions of the data at these 2 different points in time, and you can access either of them whenever you want. So this thing is actually just as a side plug, it's available as a Spark package called index.rdd. So you can actually use this to update RDDs already. But anyway, so Tegra uses this kind of neat trick to store graphs as well. Okay, so now this so-called graph snapshot index, which is using this persistent adaptive radix tree to store graph versions, it's basically a modification of GraphX, where it consists of a bunch of partitions that hold the graph, similar to in GraphX, and then each partition holds like one of these structures for the vertex table, and then another one for the edges. And there's also sort of a separate component that ensures that all of these different versions have a way to consistently reference them, which is the Snapshot ID manager. Oh, yeah. Okay. One interesting thing is that it's also possible to actually use the same idea to store just a certain window or a certain slice in time of a graph, not just like a whole snapshot of a graph. So I'll just point that out and leave it at that. But there's an interesting, slightly subtle way to do that. Okay, so that was the first goal, which is just how do you simply store many different versions of a graph within a system? And the answer is you can use this interesting trick, this data structure trick. The next thing is how do you actually efficiently run an algorithm on a sequence of versions of a graph efficiently? And so there's a thing called the time-lapse abstraction that lets you do that. So first, here's kind of the background on how these typical graph processing systems let the user express computations. So the general idea is to have some atomic unit, like a vertex, on which computations are run, and then the framework lets sort of for each possible unit within the graph, the operation can be run in parallel on the whole graph. So the most common such one is this vertex-centric abstraction, where you can sort of think like a vertex and write a program that runs on each vertex and then passes messages to the other vertices. There's the animation. Okay, so now, so the problem with just straightforwardly applying this to these different graph snapshots is that you'll end up sort of running the same operation on a bunch of different versions of the same vertex, which can often be unnecessary. So in this example, I think we are. Let's see. Let's not look at the example, but just to take a simple example, if you have this three versions of this graph and you wanted to run some kind of a message passing computation on, say, vertex B, which doesn't actually change in structure, then naively you might end up running that same function 3 times, once for each of the vertices of B. Once for each of the versions of B. So instead, what we want to do is just run this once and then have some way of extending and generalizing the vertex program that the user passes in, so that it can operate on many different versions of B at the same time, and then thereby save a bunch of time. So the idea to do this is simply to sort of expose this these temporal versions of each vertex to the vertex program when it's run, and then let the user apply whatever application level semantics are necessary to make sure that this actually works. So here's kind of a representation of that, where all the different versions of each vertex get packed into one larger structure. Yeah, and this is the benefit of it. And then what this actually looks like in the code is it means that every existing graph function can just additionally take these snapshot IDs that it wants to operate on. So you can see that each of these GraphX, these are the standard GraphX API, but with this snapshot ID abstraction added to it. Okay, so in this way, it's sort of possible to execute these bulk transformations like a map on each vertex all in one go. So just if you wanted to map vertex A, just map the vertex property, then it just gets mapped once. So that's nice. Okay, so now the third thing that's interesting here is how do you express these sort of sliding window computations, which are actually pretty interesting for expressing like most network intrusion detection, or there's a whole bunch of reasons to do this, so I sort of briefly glossed over the details on how to actually store these snapshots, but given that if we actually have these the results from a previous window, then the key question of how to express windowed computation is how do you update a window as it slides forward. So there's sort of again some strawman approaches to this. One idea is that you can just rerun the same algorithm over and over again each time the window moves forward. So sort of each time you get a new batch. You can also try to sort of memorize internal parts of the computation, and you can also store sort of this operator-wise state, so-called, and there's a system called Naiad that actually tries to do this. Now, instead of doing this, what we do is just to exploit the version data structure that we have. Let's see, here's this figure. Yes, so in this example, this is just an example of how to do this for kinetic components. But again, I won't go over this too much for reasons of time. But so let's see. Oh yeah, so one interesting trick beyond that actually is that for some algorithms that are sort of machine learning or statistical in nature, some of them actually are robust to like certain perturbations in the state. So actually, if you have like for example an ongoing PageRank computation, and PageRank happens to be one of these algorithms that can tolerate some changes in the underlying data, then each time that you receive an update, you can actually just sort of use this so-called pause, shift, or zoom model, where you take the ongoing iterative PageRank operation and then just pause it, shift the graph by updating it with the new graph update, and then resuming PageRank on this updated state. And so this, I have some. So there's some performance results that show this actually works, and it actually makes things a lot faster. And here's kind of an example where if we're running PageRank and then we add a new vertex here, then we can just copy over the existing sort of the ranks and then let the algorithm keep running. And this ends up giving a big speed up for this for these kinds of specialized class of algorithms. Okay, so and then as I mentioned, the final thing that's desirable in these systems is to try and mix and match computation models, which are this graph and data parallel models. And this is actually pretty easy to enable because GraphX already was sort of built around this idea, and so it's sort of a natural thing that comes in to this new system. Okay, so now I'm going to talk about some preliminary results that Anand ran on this system Tegra. So he evaluated it on these two reasonably sized real world graphs, and they're actually the same as what GraphX was originally evaluated on. And so I'm going to be talking about showing some of the speed ups of this new system Tegra over GraphX for the cases where you have this snapshot computation. Okay, so here's this experiment, the first experiment, where sort of the goal is to try to figure out whether or not this snapshot index, this sort of structure sharing way of packing in many different snapshots into the same, into a smaller piece of memory, actually works. And so here you can see that there's on the x-axis that there's like the number of snapshots that we're storing, and then here we're sort of comparing against sort of the naive way of doing this in GraphX, which is where you repeatedly copy the graph over and over once for each snapshot, and then here each snapshot is actually being changed. 10% of the vertices and edges are being changed from one snapshot to the next, and so you can imagine that over time these snapshots won't actually all be exactly the same, and so you'll have to store some extra data to represent these changes. And in fact, you can see that here's like the reduction in memory usage compared to just storing one copy of the graph per snapshot. And initially, there's a pretty large savings, but over time, as the snapshots diverge from the original version, then there's this like decay in memory usage. Anyway, but the fact that these numbers are above 1 at all shows that this thing is actually results in a memory savings for this example. Okay, so the next thing is this experiment sort of tries to see whether that time-lapse abstraction actually is able to save runtime, So here we're running the connected components algorithm on a sequence of batches or snapshots, and then again we're just comparing naively to sort of in GraphX we could restart the whole graph, the whole computation from scratch on the new input versus using the existing results partially along with this. The time-lapse abstraction, which lets the connected components algorithm actually see, here's the same vertex at all of its past in all of its past versions, and then how, based on that, whether or not to send a message, for example. So again, you can see that this actually helps compared to the naive thing. And then again, there's the same pattern of over time, the speed up just sort of asymptotes to some amount. Okay, and then finally, this is kind of an interesting example where we're doing that pause, shift, resume algorithm approach for PageRank. So here, the setup is that we have PageRank, and then we're evaluating it over a sequence of of updates again. But for the subsequent updates after the first batch, we're actually just copying over the PageRank algorithm state and then letting it continue to run to convergence. And so it turns out that PageRank actually, first of all, does converge even despite the graph having changed slightly underneath it. And then also it converges actually quite a lot faster than just starting the algorithm from scratch. So again, this is kind of a neat. Oh, and so if we didn't have this pause, shift, resume thing, then in each time interval we would take the full 220 seconds to get the current result. So I'll just emphasize that this is a pretty specialized thing. Like most algorithms won't be robust to this kind of a change, but in the case where it does work, it's a pretty cool savings. Okay, so I think that's all I have. So yes, so this is the summary. There's new system Tegra, and it's able to support processing time-evolving graphs efficiently. And there are a few interesting things that Anand is still working on. So one of them is to expand this sort of same abstraction to other research paradigms. So the popular paradigm in industry is a vertex-centric model, but there are actually other things like a subgraph-centric model and others that are better suited to expressing various other algorithms. One other thing is there's this related system called graph frames, which I'm working on. So I actually have a talk tomorrow on that. But it's one thing that Anand is interested in working on next is adding support for querying a time-evolving graph. Yes, there's a code base that hasn't been released yet, but he plans to open source it soon. Okay, so that's all I have. I'm happy to take questions now.
Yeah, we've got plenty of time for questions, so let me run the mic over to you.
Hi, so this question may be a prelude to what you're talking about tomorrow, but when graph frames is kind of fully developed and out, will it utilize some of these algorithms internal with it?
Okay, so these algorithms are just purely related to processing time-evolving graphs. And graph frames currently we aren't focusing on that. We're actually one way to get the same effect possibly is that we're sort of collaborating with the people from Neo4j on supporting better integration with Neo4j. So the idea there is that if you have a graph that's actually updating, that's evolving, then Neo4j is actually very well suited to making these transactional updates. And so you can actually run a graph query and then kind of choose whether or not to run it on graph frames or Neo4j based on the staleness of what you want.
Okay, thank you.
Another question? Pardon me. Sneak across here.
Hi, great talk. This might be going a little bit in the weeds, but when you showed the first slide with the memory improvements, at some point after a few cycles, the amount of memory consumed actually went down, which seems to suggest somehow it's non-deterministic or lossy or something. Like I couldn't figure out, I don't know, it looks like snapshot number 7 or whatever. Like how does that happen?
Well, so I think so it's not the amount of it's actually it's a factor of the memory usage. So it's like there is, I mean, like the y-axis here is the reduction in memory usage compared to storing every snapshot on its own with GraphX. And so one reason why this like factor could actually go down is that I mean these deltas are being generated randomly. So there's sort of an interesting property of the data structure underneath that's being used to store all the different versions. That if the updates are kind of clustered into one particular part of the graph or like one section of some contiguous set of vertices, then that'll actually it'll result in a smaller update footprint size than if they're like randomly scattered all over. So my guess, not having run the experiment myself, but my guess would be that the updates themselves are what's like the sort of pattern of how the updates are generated is what's causing that.
Over here. So great talk. So the snapshots that you described, you kind of focused on time evolving
graph models. Can you speak to the option of using this for multiple kind of what-if scenarios instead, like being able to assess large numbers of hypothetical perturbations of the graph?
Yeah, actually, that's a use case that I'm personally interested in. I think there first of all isn't quite as natural of a fit because in those kinds of scenarios, you know, it's not always the case that an update is going to be very sparse. Whereas with a time evolving graph, you expect that, like, for a large enough graph, each like, say 5-second window will only touch a small portion of the graph, and so it's possible to efficiently compress those deltas using that trick. But still, I mean, for certain kinds of what-if scenarios, I think the same approach could work perfectly well. I think that also the bulk of this work isn't just about representing the graph in memory, but also about making the programming model kind of friendly to expressing these kinds of algorithms. And so there, it might be a little different. But I'd be interested in talking afterwards about this.
Yeah. So my question is that can you please specify some use cases where this kind of time-changing, time-variant graphics kind of model will basically work, or some business scenario that where this kind of computation will be necessary?
Sure. Well, Anand actually, the thing he's interested in, he's a student who's been working on like wireless computation for a while, or sorry, wireless networks for a while, therefore his interest is mostly in how we can apply this to cell networks, and so he actually, I think, did work with Bell Labs or something, for answering those very questions that I was talking about earlier. But of course, time evolving graphs, I think, are a pretty widely useful thing. So the example I always use is like, it's not exactly a business application necessarily, but if Facebook wants to, there are some researchers or analysts at Facebook who want to track statistics about the social network, or things like engagement. Those can all be expressed as graph queries or graph algorithms on this time evolving social graph.
Any more questions? Here's one.
Hi, great talk. And I saw you mentioned fraud detection in the end of your talk. Can you speak something about how this evolving graph can apply to fraud detection?
Okay, sure. So I'm not like a big expert on fraud detection or anything, but so some things that I've seen for fraud detection, people seem to use it for to run clustering algorithms, or to run like network centrality estimation, or there's connectedness. So I mean, my understanding is that people tend to apply. There's a certain set of well-studied algorithms that kind of can be squeezed into giving answers for a whole bunch of domains, and fraud detection is kind of one of those that there's a whole variety of graph algorithms for which fraud detection can use.
More questions? Anyone? All right, thanks, Ankur.